All right, a lot of announcements to start off with today. It is advising day on Wednesday, so hopefully your advisor will contact you with an email or something about coming to meet with them, or I've forgotten to actually myself with my advisors so far, but you can also reach out to your advisor and say, hey, what time on Wednesday are you open to meet? I'd like to meet, and they can get back to you about that too. So you should be thinking about your schedule for interim and spring before you meet with them, so that you have an idea of what you want to do, and then they can advise you about those things. Again, I still haven't heard from some people. I've heard from most of you, but there's still people I haven't heard from. I would like to know just whether or not you want to take differential equations in the spring. Again, the levels were like very sure, somewhat sure, probably not, and definitely not, with 4 different ways. Phrase it as far as whether you think that's going to be the case. If we have enough demand, I might offer an online section of the ideas there, so we want to get an idea of what the demand will be. It's not set in stone, but I'm planning on a math course next summer, if the administration approves it, to help people take an actuarial exam in financial math. As far as meeting times go, actually I think it can be very flexible. I'm imagining if this course does run that we might only get 2 or 3 or 4 people that are interested. That's fine. If we can't even meet all the time at regular schedules, we can meet periodically. The main focus will be helping you study for the financial math and actuarial science if you are interested in such a career. And that can help you get internships if you do well on that test too. Next week, or this week, is a good time to pass the gateway. Still, some people need to pass the gateway. You know who you are. It would be good to practice with advising day being on Wednesday to take the gateway tomorrow or Wednesday or Thursday or Friday, for that matter. Study and try to pass. You know who you are, and I do know who you are. I got it recorded. You have a question?
I was going to ask about the financial math course. Would that be like an accredited course, or would it be like a skills course?
It would be for credit. You would get credit for it, which does mean you'd have to pay for it, but it would help you study for the financial math actuarial exam. You'd have to do studying beyond the course, or you'd have to study in the course really intensely to be able to pass the exam. But that would be the idea, is if you really want to be an actuary, you would want to take that exam and pass it. Yeah, it would be for credit. It's not required in any major, but it does give you math credit, elective credit, and it'll be a 200 level math class. The lectures today, I think we can do it in 2 because this camera doesn't seem to be splicing my lectures so quickly. Lecture A is going to be another actuarial present value example, and you will have 1 problem to do for Friday that'll be on actuarial present value. Talk more about sequences and convergence of sequences, and that'll flow into lecture B, as well as more about geometric series in lecture B. So, what we've done so far with actuarial present value has been for a single payment. That's what we did before. We said a washing machine might last so long, and then the company's going to pay a warranty, pay you a benefit when the washing machine breaks. That is an actuarial present value of a single payment. What about the actuarial present value of something else, like an income stream or a cash flow is the other word for that? When might that be useful? Well, as a company, if you imagine, if you're a really big multinational company and you've got flows of income coming into your coffers over time, and you have expectations about that over the future, you plan to grow, for example, and you have expectations about interest rates, you might wonder what the present value of all your future income will be. That would be one application. Another more down-to-earth application for people is to get income from some kind of annuity. Now, most likely that's going to be paid monthly. You get 1 payment every month. But for the sake of making it doable for us, we could imagine you're paid continuously. Money's going into your bank account every second of every day. Now, the example we're going to consider is a very small amount. The income stream is going to be $1,000 per year that you're going to get, that's very small. That's only $3 or so a day, which would be, you know, what, every hour that would be what, $3 divided by 24, about 1/8 of a dollar, 12 to 13 cents every hour. Okay, so it's not a whole lot of money. But for the sake of keeping the numbers manageable, let's go ahead and pretend that that's the case. So you're getting money continuously from some retirement account, some small retirement account, once you retire for the rest of your life. Let's say, I mean, I hope when you retire you could live more than 20 more years, but to keep it simple, we will go ahead and assume you only live 20 more years, and then there's a drop dead date. You're going to die before your 85th birthday, I guess, if you retire at 65. Which, you know, more and more people think they're not going to retire at 65 anymore. I don't think I'm going to retire at 65. I think I'm going to be at least 70 before I retire. And so again, to keep the model simple, we're going to suppose you die within 20 years. So we're going to have the lifetime be once again uniform. That'll be our first example at least. So the PDF is horizontal. And if it's going to be a 20-year lifetime, to get the area to be 1, we need the height to be 1/10. Not 1/20, excuse me. Sorry, I was thinking of a triangle there. One over omega in the notation on the screen, omega being the maximum lifetime left here. It's going to be a uniform distribution. To make the area equal to 1, you need to make the height equal to 1/20. So again, this is the little f of t. The capital F of t you get by integrating this. And it's an antiderivative that has to go through the origin. It's going to be t over 20. Now, again, it's an income stream. So you're not talking about finding the present value of one future payment. It's not one future payment that we're grabbing and pulling back to the present to find the present value. It's a continuous income stream. Now we've talked about present values of continuous income streams, right? They were integrals. They can be imagined as chopping up the interval into a bunch of little tiny pieces of width delta t, thinking about how much money you get during that small amount of time and taking the present value of that, pulling it back to time 0 by multiplying by e to the negative rt. But then you do that over the entire time interval, that means you ultimately have to do an integral in the end. And here's the kind of integral you do. $1,000 is your income stream in dollars per year. And e to the negative 0.05 t for a given moment in time pulls a small amount of that back to time 0. Finds the present value of it. By integrating, you're finding the present value of the entire income stream. Now, if it's $1,000 a year for 20 years, the dollar amount you get paid would be $20,000, 1,000 times 20. But the present value is going to be smaller because the present value represents what that money's worth right now. It's got to be smaller because you couldn't invest that money right now to make it grow. The present value is going to be smaller than the whole amount of the income stream that you get. But t here, in this integral, the capital T is a random variable. It's your lifetime. You're retired, you might live 5 more years, 6 more years, 11 more years, 18 more years, 17.326 years. You're going to die by 20 years in this model. You don't know what it is. That's a random variable. So this integral is really a random variable. We're going to call it y because that's what actuaries call it. Another one we call it z because that's what actuaries call it. Why would we pick those letters? I don't know. Don't worry about it. It's a random variable. What do you want to know about random variables? You want to know their distribution, meaning you want to know their PDF or CDF. The formula for the probability density function, you can find probabilities by integrating. The formula for the CDF, cumulative distribution function, you can find probabilities by subtracting. Because the CDF is a big F, it's an antiderivative of the PDF. And you might want to find things like means and medians. By doing this integral, you can simplify the formula for y in terms of t. And that's now not too different from the other formula we had for z in terms of t. From last week, z was 1,000 e to the negative 0.05 t. That was the formula for the present value of one payment of $1,000 in the future time t. This formula is not that different. Still involves an e to the negative 0.05 t and a number in front of there, but now you are subtracting that from 20,000. It is different, just not a ton different. Probably should be doable still. You can write this without an integral sign. That's kind of cool. What are the values that y can take on? It's got to be between 0 and 20,000 minus 20,000 over e. Why? Well, if you, imagine you retire, okay, and you die the second you retire. Sorry. The present value of your future income stream is 0. You got nothing. On the other hand, you could retire and you can live for 20 years and then you die. So that would be the biggest possible present value. That would be what you get when you plug in t equals 20. Or what does that equal? 20 times negative 0.05 is negative 1. It equals 20,000 minus 20,000 e to the negative 1, which is about 12,642.4. That's the biggest possible present value of your future payments if you live exactly 20 years in this model. What's the probability of y being between 6,000 and 8,000, for example? What's the mean? What's the median? Okay, so just like before, we have to figure out the CDF first. I'm using y's instead of z's now. Here's the most fundamental equation. If capital G is the CDF, cumulative distribution function for capital Y, it is a probability. It's a probability of the variable being less than or equal to the given number. Think of capital Y as the random variable. That's the quantity that's unknown. And it's random. Who knows what it's going to be? It's going to be different for different people. You think of the little y as being a specific number. When you think about this equation, it's probably best to think of y, the little y, as being a specific number. And at the very end, then you say, oh, y could have been anything, so it's a variable. That's the best way to view this, conceptually speaking, so you don't get confused.
So is big Y then our given number?
Big Y is the random variable. For a given person, it represents the present value of the future income stream that they are getting until they die. They don't know when they're going to die. Nobody does. They could live 10 years, 15 years, etc. So nobody knows what the present value is exactly. But it can be modeled as a random variable, and you can find out things about that random variable that helps companies, for example, make business decisions based on having a lot of customers. You can make business decisions based on these things. Okay? So these are real practical. This is real practical stuff. It's high-level stuff, but it's really, really practical. You can do the same kind of algebra as before. Replace y with its formula in terms of t right there. That's what I did there. Just like before, solve that for capital T. Do some algebra. What did I do here? First, I divided both sides by 20,000 to get this. Still inside the probability symbol. I'm doing all my algebra inside the parentheses here. The probability symbol just gets carried along. What did I do next? I did two steps next to get from here to here. You might even say it was 3 steps. I added e to the negative 0.05 t to both sides. Put it essentially over there. I subtracted y over 20,000 from both sides. Maybe even 4 steps. Then I subtracted the fractions, and then I took the natural log. I probably should have shown one more step at least. Can you follow? I'm trying to solve for capital T here. I added e to the negative 0.05 t to both sides, so it cancels on the left here. I subtracted this from both sides. I subtracted my fractions to get the 20,000 minus y over 20,000. Then I took the log of both sides. The inequality was a less than or equal to here and a greater than or equal to here because I also switched the sides of where the capital T was. 5 steps at once. Probably should spend time after class filling in those steps to make sure you believe that. Then I divided both sides by negative 0.05, which is the same as multiplying both sides by negative 20, and got this, and the inequality switched back. And this is actually a little simpler than the other example because you don't have to think about doing 1 minus a probability to calculate this. Right? We talked about how the probability, if the probability of rain tomorrow is 0.3, then the probability it won't rain is 1 minus 0.3, 0.7. I don't have to do that here. There's no 1 minus f. The p changes to an f. Why? Because capital F is a CDF, cumulative distribution function. It is a probability. I didn't use probability notation up here, but it is. It's the probability that capital T is less than or equal to little t. So, yeah, that was a source of confusion for people, but that's what's going on here. The capital F is a probability, so you can replace P by capital F. Mm-hmm.
So I'm just wondering, why would you replace P with a capital F?
So I can use the formula for capital F. This stuff is just sort of general facts about probability. Now I say, hey, I want to use the formula for capital F because capital F is related to T. It's not related to some other variable. I could do these kinds of algebra steps with some other quantity not related to T, but T is already a variable that is your lifetime that I know something about. I know what little f of T is for that variable and capital F is for that variable. So now I want to relate it to that. And because this is a probability that capital T is less than or equal to something, and that's what capital F represents, this is a probability of capital T being less than or equal to little t. This thing represents the little t. So this probability can be calculated by plugging that thing into capital F, like that. And again, for you, this is still the same for you. On your one homework problem, like this for Friday, to this point, it's the exact same calculations, just like with those other examples from last week. It becomes different from this point on, because your capital F will be different. You will have a different capital F. You'll have a different CDF for your lifetime capital T. But this stuff up here is all the same. But here again is my capital F for this function, for this variable, T over 20. So I plug this in, I take that and divide it by 20. The 20s cancel. You also have a -1 there. By properties of logarithms, that -1 can go into the exponent of the thing inside the log, which means you can flip it. And also by properties of logarithms, you can write that this way. So this is the CDF, capital G, for Y, this present value of the income stream for the rest of your life. What's the PDF? Take the derivative. When you have it in this form, it's a little easier to take the derivative. You get that, you get negative signs canceling because of the chain rule there, and so they go away. You can write it like this, over this domain, and you can graph it. And I did double check that the integral of G, little g, there's the graph. I did double check the integral of little g is 1. It is a PDF. Okay? Probability density function, where it's higher, the data that it's modeling would be more dense, so it's higher over here in the higher values. If we simulated data for this, the data would be more dense over here than it is over here. More high values compared to low values. Does that make intuitive sense? You're going to get higher values if you live longer. Not sure it makes complete intuitive sense since the distribution is uniform. It might be related to the exponential nature of the pulling back of present values. I'm sure it is related to that. But it's not completely intuitive. It's not completely obvious that the graph is going to look like this. So that's good. You've discovered something that's not completely obvious. Whenever in math you can find something that's not completely obvious, that's a significant thing. What's the probability of y being between 6,000 and 8,000? It would be the area under this graph from 6,000 to 8,000. You can do it as an integral. You can also do it as a subtraction with capital G. It's about 0.154. And just for extra confirmation, I'll do it as an integral as well. Once again, you'll be able to use Mathematica whenever you want on your problem. Just make it clear to the grader, you know, what are you calculating with Mathematica? What integral, what equation are you solving, what derivative are you calculating, that kind of thing. The integral should be the same. Yep. What about the mean? Oh, I gave it away there. Well, I guess I said the answer over here anyway. You always integrate over the domain x times f of x, or in this case, y times g of y. In the case from last week, it was z times g of z. That's how you calculate means. They're centers of masses for the PDF, as if the PDF, if the region under the PDF were a sheet of metal, it's the center of mass in the x direction. That's what a mean is. Do the integral, ends up being about 7,358. On this graph, 7,358. So yeah, if this was a sheet of metal, the graph would balance right about there. And that's the more important thing than the median is in terms of practical application. This is saying, you know, if you are an annuity company that is giving people money, I mean, they have to invest with you first. They have to be making deposits during their working life from like age 25 to age 65 or so, and then you pay, the annuity company pays them back. They need to know on average how much they're going to pay people back as far as their present value goes. So how much money should they have on hand right now is kind of the idea. Though of course they actually want more money because they want to make a profit. They want to cover their costs. This is sort of a baseline, minimum amount per person that they need to make sure they can cover everybody's annuities for their entire lives. So it's a real practical thing. And the median can be found by solving the algebra equation. It ends up being a little bigger than the mean. Yeah, the median's a little bit bigger than the mean. The median is the point of half the area being to the left and half the area being to the right. This distribution is called left skewed. Sort of the main bulk of it is here, but there's sort of a long tail, so to speak. Kind of a thick one. Sometimes it's not so thick. Sometimes the graph goes down very rapidly. And that affects the mean more than the median, and so the mean is smaller than the median for an example like this. But the mean is a more important thing, practically speaking, in this kind of problem at least. And you can simulate this stuff. Here's a simulation. I didn't shade the areas, but A was 0 and B was 7,000, so this 0.43 is the probability that the present value would be between 0 and 7,000. 37 out of 100 data points are between 0 and 7,000. You can see the points are more dense over there where the density is higher than they are over here. But again, different simulations produce different results because of their random nature. Now we got a lot more points in the low regions on that one. The red dot is the mean. It's a running mean. It averages the data themselves, so it moves. But you can see, at least for this simulation, it's pretty close to 7,300. It looks like it's more like about 7,100 there, that red dot. There. Okay? So the simulation helps bring the probability to life. Helps you understand the meaning of it better. Because, you know, probability is just a number. 0.2 or 0.3, well, what does that mean? Simulation and comparing with data, that helps bring it to life. Helps you understand the meaning better. All right. So you'll have one problem like that for Friday. Now we're going to go back to chapter 9, convergence of sequences, and also more on geometric series. So we talked last time about how sequences can be defined typically either with direct formulas or indirect formulas, more commonly called recursive formulas. So a direct formula is something like this. Sn equals 3 times negative 1 to the n plus 4 times, oh, I don't know, negative 1. That'll be something interesting to do here. To the n squared. No, that wouldn't necessarily be real interesting. I'll just put an n plus 1 here. I'm not sure what might be interesting to do there. Divide by n. That would be an example of a direct formula for a sequence. To find the nth term in the sequence, you just plug the number n into the formula, n being a whole number, in this case a positive integer, 1, 2, 3, 4, 5, 6, 7, etc. S1 would be 3 times negative 1, because negative 1 to the first power is negative 1, but I'll go ahead and put a first power there anyway. Plus 4 times negative 1 squared, divided by 1, so that'll be negative 3 plus 4 over 1 is 1. S2 would be 3 times negative 1 squared plus 4 times negative 1 to the third, divided by 2. That simplifies to 3 minus 4 over 2, which is negative 1/2. S3 would end up being, I hope you can see, negative 3 plus 4 over 3, which is positive 1/3. And it seems like maybe this is generating a sequence 1, negative 1/2, positive 1/3, negative 1/4, positive 1/5, negative 1/6, positive 1/7, etc. This sequence is bouncing back and forth between negative and positive numbers. We are going to get that every time. It's going to be a plus or minus 1 on top, and the bottom keeps going up by 1. I'm glad that happened. That's a pretty common sequence to think about. Does it converge? What do you think I mean by converge? We can ask whether it converges or not. When do I use the word converge? We've used it before.
It goes to like one value.
It goes to a single value. You want to say something? Has a limit. We've used the word converge or diverge with improper integrals before. Does the limit exist or not? When the limit exists, we say it converges. When the limit does not exist, we say it diverges. Does this appear to be converging? Yeah, it's getting closer and closer to 0 as n gets larger and larger. Actually, a simpler formula for this exact same sequence could be pretty easily found to be, let's see, we're starting out positive when n is 1, so I can do negative 1 to the n plus 1 over n. That would be a simpler formula for this very same sequence. How would we prove it converges to 0? Claim that this converges, this sequence converges to 0. It's implicit that it's as n goes to infinity, but I'll go ahead and write that anyways. As n arrow infinity, as n gets larger and larger without bound is a little bit more precise way to say that. idea how you might prove that?
11. Limit is n approaches infinity.
Well, that would be notation that says we think the answer is 0 if we wrote down a limit sign. I mean, you look at this expression and it seems pretty clear that the answer should be 0. But if I write this equals 0, I really am assuming it converges to 0. I'm not really proving anything there. Is there really anything to prove? Well, yeah, technically speaking, let me put the definition over here. To prove, I put these green markers out before class and they were working great. Let's see. To prove a sequence Sn converges to some number L, maybe zoom in on that, is it very clear? Is it okay? We must show that the distance between Sn and L on a number line can be made as small as you like. Now, how do you find the distance between two numbers on a number line without just looking at the picture? It's the absolute value of their difference. If 7 is bigger than -5, so you can calculate that distance by doing 7 minus -5, which is positive 12. Take the bigger number minus the smaller number. But you actually can get the same answer by doing the smaller number minus the bigger, as long as you take the absolute value. This already gives you a positive number, so you can also put absolute value signs around that. In general, when you don't know which number is bigger than the other, to guarantee that you're going to get the distance between the numbers, take the absolute value of their difference. So we must show the distance between Sn and L as represented by that expression there can be made as small as we like by taking the n to be big enough. Sufficiently large is the official way to say it. By taking n sufficiently large, we can make the distance between Sn and L, represented symbolically by that, as small as you like by taking n big enough. Question?
Couldn't you do the same thing though with something that diverges? Like at some point it starts diverging, couldn't you find also?
Well, you can always find the distance between any two numbers. You just can't necessarily make it as small as you like. That's the key here. Let's take our break here right now. After break, we will dive into this with this example and some other examples.